Here we are again, here for number 6. Got 9 for you. Reviews total. This will knock out number 6, so we're getting there. You'll see here as we look through what's going to go on, it says miscellaneous topics. There's no real common theme with all of this. Some random things kind of pop in here and there. All of which, though, again, just to cover all your bases you're going to want to know. So at the top, you'll see where it says curve sketching. This asks you to graph these without using your calculator. So the ones that you would have to be concerned about, this will be a good review. I do want to do this one. The one that you'll have to be concerned about and what they've done to not have to worry about a calculator, and that you've seen these before when I give you a table, and then it gives you x, f, f prime, f double prime, so on and so forth, and I give you all these values, and you have to take those values, graph your equation, or graph your function. So that's how they would give you this. So we'll do one or two. We don't have to spend too much time on this because this just isn't going to be a whole lot of something that you're going to need to be able to do without a calculator, just to refresh our memory on some things. So what you'll first recognize is that we have in this first one some excluded values here. So with this, a rational function, we're going to have vertical and horizontal asymptotes. Our vertical asymptote in this case are your excluded values, +2 and -2. And then your horizontal asymptote, the way we do that, kind of what we've been doing now with the end term test for a while, is we find our limit as x goes to infinity or -infinity. So it could also be approaching a -infinity. In this instance, since our denominator has the bigger degree, that limit's going to be a 0, so our horizontal asymptote would have to be a 0. So if we were going to graph this, we know the x-axis is acting as our horizontal asymptote, and we know we have a vertical asymptote at 2 and -2. The next thing we did with these, we want to get as many points as possible so we don't have to guess too much what this would look like. We wanted to figure out our x and our y intercepts. So if I wanted the x-intercept, you're going to let y be a 0. Let me do it up here. So if we let this y be a 0 here, try to solve this equation, we would take our denominator and multiply it over. That would still give us a 0 on the left. The only thing left over on the right is a -8. Those are not equal to each other. It tells us we do not have an x-intercept. We should not be touching the x-axis at all, since that's our x-intercept. The y-intercept, though, usually is pretty simple. For the y-intercept, you're going to let x be a 0. So if we come up here and let x be a 0, you would get -8 divided by -4. We know we cross the y-axis at 2. From that point, we then had to figure out what are our critical points, like where are we increasing and decreasing. We do all that through our first derivative. So if we took the derivative of this, most of you probably do a quotient rule here. Take your denominator, the derivative of the top would be 0, minus the top, so the -8 stays the same. The derivative of your denominator is 2x. All of that gets divided by your denominator squared. Set that equal to 0, we would simplify the numerator. Those would drop out because of that 0. The rest of those terms should reduce down to be a 16x, +16x, all over your denominator squared. One of the reasons I still like to do this problem, when we go to find test points, which is our next step, a lot of times our derivative equals 0. That's typically what we're looking for and solving for, and that will happen here. So if I take this and multiply your denominator over, I would get 0 equals 16x. Solve that, x is going to be a 0, so that's going to be a test point. That's common. We've done a ton of those that we should definitely know. But the other test points that we have to be concerned about is where our derivative might equal 0. If we look at this problem, and we did a few of these the other day in that previous review, I think 3 or 4, you'll see that we have a couple of places where your derivative is undefined. If x is a 2 or a -2, that would make your derivative undefined. And the reason for that in this problem is, if you notice, you have some vertical asymptotes. So discontinuities are one of the 3 things that would cause a derivative to be undefined. So those are our test points, -2, 0, and 2. When we did these with fractions, we just talked about sort of what's happening in our numerator, what's happening in our denominator. So if we look at this derivative, your denominator is always going to be positive. No matter what I plug in here, you're going to square it, making your denominator always a positive value. In the numerator, since it's 16 times x, if I plug in a negative x value, it's going to be negative. So anywhere to the left of 0, where I have negative x values, I know my derivative would be negative. If I'm going to go to the right of 0, now my x values are going to be positive. So if I come over here to the derivative, if I let my x's be positive, now that numerator will always be positive as well, telling us that any positive x values should result in a positive first derivative. We can then come over here, graph this. Sometimes we wanted our second derivative. When we had asymptotes, we skipped that step, because if we understand the behavior of asymptotes, we should be able to take that idea along with our now sign chart and sketch out what is happening. So since these are asymptotes, a horizontal asymptote, when you tell me that there's a horizontal asymptote of y equals 0, that means the further and further left we get, our graph should be approaching the horizontal asymptote. So that means our graph should either be right on top of this thing, the further left we go, or our graph should be right below that asymptote, the further left we go. So it has to be doing one of those two things. If we then come down here to our sign chart and understand that we're negative, before we do that actually, with the horizontal asymptote, we're right on top of it from below or above. As we move further right, then we can't cross a vertical asymptote, so we'd eventually have to shoot straight up this guy. Or if we're moving in this direction, we'd have to be shooting straight down along that vertical asymptote. So we have to be leaving the horizontal asymptote, approaching the vertical asymptote. If we then now come to our derivative and identify that in the first interval here, that our first derivative is a negative, meaning our function has to be decreasing, that would mean that we are down here. So that's why we don't necessarily need our second derivative. If we now go in between, if you notice, we have a minimum at x equals 0. Our first derivative is changing from negative to positive here in these intervals. So we know we have a minimum at 0. When we were to sketch these, we would know what is the y value at 0. We know that. That is actually our y-intercept. We already have it plotted. We are decreasing to the left. Well, if we're decreasing, that means we have to be leaving this asymptote from up here really, really close, but we also should be decreasing towards this point. After that point, your derivative changes positive, so we would have to be increasing to the right of that point and approaching this vertical asymptote. Notice how you get a minimum here, just like we're supposed to based upon our sign chart and our change. If we go to the right of 2, our derivative is always positive. We've got to be increasing. We've also got to be leaving the vertical asymptote and approaching the horizontal. So we're either doing this, leaving the vertical and leveling out towards the horizontal, or here, close to the vertical, but leveling out towards the horizontal. Our derivative is positive. That means our function has to be increasing. Of those two, the one that's decreasing is the one on the bottom, so that would have to be our graph. Okay? All right. 2. If I can get this thing to move, there we go. I'm just going to have you do some asymptotes just to make sure we're squared away on that. Vertical asymptotes are always where our excluded value is, or what our excluded value is. In that problem here, x cannot equal 5, so it's a vertical line, so we would write it as a line. X equals 5 is our vertical asymptote. The horizontal asymptote we find by finding the limit as x goes to a positive or a negative infinity. Either way, the limit, whether x is going to a positive infinity or negative infinity, I don't know why I wrote this. This should be as x goes to a positive or negative infinity. Your limit should be a positive 1. Some of you may be wondering about oblique asymptotes. I had you do that. Oblique asymptotes are not an AP topic, so no need to really worry about those. That was just me being mean. Vertical asymptote, horizontal asymptote for number 3. Our vertical asymptote would be a positive and a negative 5. Our horizontal asymptote, we basically ask this thing what happens as we go to a positive infinity for x or a negative infinity for x. The bigger degree is in our denominator, so this limit would be a 0. Or horizontal asymptote is 0. If we, okay, I got a couple of 4s here. Skip this 4 for a minute. If we answered number 4 real quick, it's another asymptote question. If y equals 7 is a horizontal asymptote of a rational function, so it's kind of the exact opposite of what they normally do. Normally, here's your function, give me the asymptote. Here they're now giving you the asymptote, and then asking you which of these could be a true statement. So if y equals 7 is a horizontal asymptote of some function f, which of the following could be true? So what they're telling you is, if we have a horizontal asymptote, what that means is we had to have had a limit as x goes to infinity, or a limit as x go to a negative infinity for that function, and that limit had to be 7. So we have a couple that were candidates initially. Here's one that's asking as x goes to infinity. Here's one that's asking as x goes to a negative infinity. That's the way we always figure out our horizontal. The one that actually gives us a limit of 7 is B. So there's a little curve sketching, a little review of some asymptotes. We see that. Hopefully we can recall those. All right. So now number 4 I do want to do all the way through. Notice how there are no asymptotes here. There's no excluded value in our denominator. It's not a rational function. So we don't have to worry about asymptotes. We would still start this off looking for intercepts. So if I wanted the x-intercept and you wanted to solve this, where could I do this? I'm going to do this way up here so I have some space. Sorry, it's hard to write small with this thing. And I'm going to let y be a 0 when x is a 1/3. If we solve that, move your 3 over. This is a cubed root of x. So in the next step, you would cube everything, and we get an x-intercept of -27. So on our graph that we're going to create, way over here to -27 is our x-intercept. If we want the y-intercept, let your y be a 0. That's easy then. If y is a 0, our y-intercept is 3. So we come over here, and at the y value of 3, we have a y-intercept. So from this step, let me just make it bigger so my writing looks smaller. So our next step, figure out what are our critical points. So we take our derivative. So that would give us x, or 1/3 x to the -2/3. Set that equal to 0. Simplify this. So you'll have your 1/3. The negative exponent tells us to put into our denominator. And then this would be a cubed root of x squared. If we now want to test this, both things we want to consider. Where does our derivative equal 0? So that's what we would try and solve right here. Similar to one of the ones we did above, though, if you took your denominator and multiplied that over, you would end up with 0 on the left and a 1 on the right. Those are not true, or that statement is not true. What that tells you is when we come over here to graph our equation, we shouldn't get anywhere where we get a nice horizontal tangent line. We should have no slopes of 0. Don't forget, however, which is easy to do because most of the time the ones that we're dealing with is when the derivatives equal 0. We also need to consider, when is our derivative undefined? In this instance, your derivative is undefined at 0. So we do need to test that. This is pretty straightforward. If you look at your fraction for the derivative, the numerator is always a positive 1. Your denominator would also always be a positive 1. I'm sorry, always a positive number. What happens? You have a positive over a positive. So our derivative is always positive. What that should tell us is when we go to graph this, there's no max, there's no min. Our graph should always be increasing. With these, we definitely want a second derivative. We want to know what our shape looks like. So I would do it with this one. So take your second derivative now. That would be a -2/9 x to the -5/3. We would set that equal to 0, simplify this expression, and should get a -2/9, and then in your denominator should be the cube root of x to the 5th. Same thing would happen that happens in the first derivative. If we multiply this over and try and solve it, you won't get a test point from there. You'll get 0 equals a -2, so we don't have to worry about that giving us a point to test. But in our second derivative will be undefined at 0, just like the first derivative was. When we do our derivative test, we can look at the second derivative. No, it's always a -2, so that'll always be negative. Our denominator, though, will change signs. So if we take a -1 and plug it in, so if I plug in a -1, raise it to the 5th power, it remains negative. The cube root of that -1 will be negative. So overall, the denominator is a negative, telling us that the second derivative would be positive to the left of 0. To the right of 0, numerator for the second derivative is always negative, but if I now plug in a 1 to my denominator, our denominator would be a positive value. So overall, the right-hand side of 0 should give us a negative second derivative. So that means we have a point of inflection at x equals 0, and then we would want to know what is that point. We've already got that point. It's our y-intercept, so you plug that in, you get the y value of 3. So this should be a point of inflection. So keep in mind, points of inflection aren't just when the second derivative is a 0, it can also be when it's undefined. You just need to make sure you get a sign change. We very clearly have a sign change in our second derivative here. I would then have you graph these. I would have had you look at this, look at this, put those two ideas together and sketch that. So if you wanted to see if you can do that, you can pause me, try that, see if we can come up with this. When we go to do that, what should be happening is the first derivative told us we were always increasing. So that's us increasing. But while we were increasing to the left of 0 here, our second derivative was positive. So we should have been concave up. So as best I can squeeze this in here, we would have been concave up as we did that. So to the left of 0, so here's our 0. To the left of 0, we're increasing concave up. To the right of 0, our first derivative told us we have to continue to increase, but now we should change to being concave down. So from this point, we'd continue to increase and we'd be concave down. Then what I had you, or what we talked about, we actually did one similar to this before. Our derivative was undefined. That's how we got this test point. The 0 was making our derivative undefined. So what that means is you better have a sharp corner, a vertical tangent, or a discontinuity happening at the x value of 0. In the first one we did, we had vertical asymptotes. That's what was making our derivative undefined. In this one, what you should notice is what almost certainly was happening then, I could probably help out or draw this a little better, we were going vertical at this point, and that's, for that one instant, what was causing our derivative to be undefined. All right. So there's a little review of some asymptotes and such. We will move along. Length of a curve. Just did one of these in that last review. If you looked at that, number 5 on that birthday cake problem. So we don't necessarily need to go through all of this all the way. This is pretty basic, really. You just need to know this formula. I'm going to give you a formula sheet with all the major formulas. You would definitely want to have that just right in front of you on the day of the test, just as a quick reference. So if something pops up and you're not sure what it's asking about, you would have that. There's really not much reason to do this because it's really just memorizing a formula, being able to plug that in. So there you go. It's always the square root of 1 plus your derivative squared. So as long as you can take the derivative of this, and know the formula, then you're going to be all set. This asks for the length of the curve trace. So just understand what that's asking. If we want the length of the curve, during the first 4 seconds, then we're just looking for the length of the curve. It was referenced as perimeter in the previous review. So a lot of different ways it can be asked in terms of the length of the curve without just coming out and saying length of a curve. But when it is, recognize it and know that we're just using this formula. Growth and decay, also not something that I would be overly concerned about. We'll do one as a quick little reference. Can't imagine this is going to make an appearance, but just to make sure that if it does, we've seen it at least once in the last 4 months. We'll go through one of these. The big idea, and the reason this is unlikely for you to see, there's 2 growth models, growth and decay and logistic growth. So logistic growth is coming up for us to review. I believe it's our 8th review, if I remember correctly, 8th or 9th. There's 2 growth models, logistic and exponential. So exponential growth is what growth and decay is based off of. This is an A-B topic. This is a BC topic. So it's unlikely, even if we were doing the test under normal circumstances, it's unlikely you would get a growth and decay question, where it would be very likely you're going to get a logistic growth question. So we talk about this, we'll go through this, but it's again not a big deal. It's not something that I would spend a ton of time on. The big thing that you might see, they might reference, is the whole expression here when it says that the rate of growth or decay is equal to, the change in the quantity of y, so that's dy over dt. So we have our population, a lot of times those are y, with respect to time, is equal to the rate, k, multiplied by the amount present. We a lot of times did it with p's for population. So our population is growing at a rate, so at a rate that's directly proportional to the population. That was our differential equation. That could make an appearance. What we then talked about is every time we separated that, that gives us this equation. That's our exponential growth equation. P of t is our population at any time. T is that time. P sub 0 is your initial population. K is the rates, 2%, 3%, or whatever. So we'll do the quick one, the short one here. Population y grows according to this differential equation. One of the things we would have talked about, they rarely will use exponential growth and decay. They won't use those words. They typically give you the differential equation, at least with the ABers. And then we would want to know, as soon as we see this is our differential equation, then we know that we're dealing with exponential growth. So the question then, if the population doubles every 10 years, so our time would have been 10, what is the value of k? K would be the variable that should be left over to solve for. You weren't given an initial population. You weren't given our population at that time. So it's one of the ones where you said p sub 0 we don't know, so we're not going to make it up. But what we do know is after 10 years, whatever our initial population is, our new population would be twice as big. So it'd be twice p sub 0. These would cancel. So you get 2 is equal to e to the 10k. Take your natural logs of both sides. And so this would give us the natural log of 2 equals 10k. Divide by 10. And that should give us that. That's exponential growth. 8, if you wanted to do this is the one you had to work back and forth. I actually just cut and paste this from our notes from the day. So if you went back to whenever we did exponential growth and decay earlier this semester, you could find this problem. It was 16,900. Not something I would spend a ton of time on, though. Inverse functions. So how they use inverse functions is it's usually like the part D or E on a free response question that's really sneaky and tricky that nobody gets right, or a very small percentage of kids get right. But if you can do it, it gives you kind of a point that other people don't get. But these are hard. When they give you these questions, they're quite tricky. So inverse functions, we should know what an inverse is. It's our x's and our y's just getting interchanged. That's not hard, but the derivative of them is what's hard. So it says the value of, and then you'll see this notation here. That's your derivative notation, but if you notice, this is our inverse notation. So that basically just means the derivative of our inverse is what this one is saying. At any point f of a is, so think of this kind of as an equal sign, is the reciprocal of the value, a little redundant there, of the value of our normal derivative at x equals a. So here's what this is getting at. I'm going to walk you through this the same way we did this in class because there's a pretty decent chance we don't remember this anyway. Method number 1, we can use the reciprocal. This is probably the easiest way if it's up to you. So if we took the derivative of this, and I'm going to ask you to do the derivative notation, or the fraction notation for this one, the change in y with respect to x would be 3x squared. Pretty simple. The reciprocal version is if I just did the reciprocal of what we just found, 1 over 3x squared, one of the properties of a function and its inverse is the derivative and the derivative of the inverse are simply reciprocals of each other. By simply taking the reciprocal of the original derivative, that will give us the derivative of the inverse. So our derivative magically becomes the derivative of the inverse by finding our reciprocal. We then would evaluate that at x equals whatever the x value is at this point, which is a 1. So we would say the derivative of our inverse for this problem is simply 1/3. So know that. Method number 2 actually makes more sense. It's actually a better proof of what we're doing. Method number 2 is actually using the inverse's derivative. So what that would imply is let's find the inverse. So we're going to switch around the x's and the y's. So do that. We then would solve for y. So we would go through, solve this for y. So I'm just going to subtract. What did I just do there? Let me fix this. We should get y cubed equals x minus a 1. Got a little excited there. Oh, here we go again. All right, let me check this. Yeah, so y cubed is equal to x minus a 1. And then we would continue solving for y. Take the cube root of both sides. Once we've solved for y, that is your inverse. So our whole goal is to take the derivative of the inverse. We now have the inverse. That just means we would want to take the derivative of this. So now that we're at this step with our inverse, we're going to take our derivative. So we're going to do the fraction notation. So that's our derivative using the inverse, or of the inverse. Over here, recognize this is just our chain rule with a power of a 1/3. So we're going to do that, 1/3. Leave the inside alone to the negative 2/3, and then the derivative of the inside would be a 1. Bring this over here. Simplify this, so we would still have our 1/3. We have that term, that quantity raised to the negative exponent, so we're going to put that into our denominator. And then when we do that, it should be a cubed root of x minus 1 squared. So now where this gets tricky, we're ready to evaluate this. So let me write this one more time just for some space to work. You don't necessarily need to recopy this. I'm just recopying it so I have a little room behind it. Is we're now ready to evaluate this at our x value. And this is where this gets sneaky. What we have done when we actually find the inverse, so from this step to this step, notice how your x's and your y's got interchanged. And when our x's and our y's get interchanged, what that's telling us is the point that we were given to work with, the point 1, 2, wouldn't even be on the inverse. So if we look at this inverse graph, or inverse equation, if you let x be a 1 and you let y be a 2, those are not going to be equivalent to each other. However, if we switch those around accordingly, so if our x's and our y's get switched in the equation, that would imply we want to switch our x's and our y's around in the point. Now this should work. If you let x be a 2, you would get, so put a 2 right here, you'll get a 1 on the right. And if you take a 1 and plug it in for your y, you'll get a 1 on the left. That's our true statement. So when we did this problem and we actually used the inverse, the x and the y and the point would also get flipped around. So the x and our new point for the inverse would actually be the y coordinate of the original point that you were given to work with. When we do that, we better get the exact same answer, and we will. We would get 1 on top, we get that 3. And then when you take this 2 and plug it in here, you would get 1 squared, which is a 1. Cube root of 1 is a 1. We would still get 1/3 as our answer. Same thing that we got over here. 10. If you think, oh, that's not that hard, I wouldn't mess that up. Try number 10 real quick. Pause me, give that guy a whirl. This still makes my head spin. I do it every year. This is an old multiple choice question. This is also, though, I promise you, very commonly, D's and E's get a little trickier on the AP test. Usually on the free response portion, the A's and the B's are pretty straightforward, hopefully. The random stuff are the D's and the E's. These are a lot of times those random topics. So if you wanted to try that, try it, but it'll make your head spin. So for this one, saying let f be a function, here's your function for f. And then they introduce a new function, g, and all they're telling you g is the inverse of f. Then they tell you that g of 2 is equal to 1. So right away, maybe make a note of this. For the function g, we know the point 2, 1 is the point that's on there. If g is the inverse of f, at some point we're dealing with the inverse, so we would know for the graph of f, the point that we know for sure is on that graph would have to be 1, 2. They're then asking you to find the derivative of g. So if we come over here, the derivative of g would be the derivative of the inverse of f. So if we go over here to f, let's go ahead and take its derivative, 3x squared plus a 1. This allows us to do that easier method. It's kind of a combo here. This is the way they test you on both methods that we just talked about. This is our original derivative. We can find that pretty easily, 3x squared plus a 1. We know then that the derivative of the inverse, we can switch this to if we do the reciprocal. So 1 over 3x squared plus a 1. All right, I'm actually going to rewrite this. That's what I pause for because I want to, it's a little clearer. We could do f prime, but let's use that fraction notation. Right now, this would just be df dx, the derivative of f with respect to x. But when we take the reciprocal, this would become the df to the negative 1, the inverse of the function f, its derivative, and it's simply the reciprocal. So we then come down here, and we now want to evaluate x. So in this problem, we are dealing with f here. So we never did interchange them. What we want to know is what is the x value on the function of f. So if we look here, the point that they gave us, your x value was a 2. But since we're dealing with the function f, our x value needed to be a 1. So our answer should have been 1/4. All right. So hopefully you got that. All right, quick little rules here. We're going to go over, I think the next packet is all of our different integration rules, the partial fractions, integration by parts, the trigonometric ones. We're going to do that in our next packet. This is just a quick little refresh on some antiderivative rules that are the one-steppers, the pretty quick ones. So some power rules and all that. So for antiderivatives, we would want to treat this as x to the negative 2, and then we know we add 1, and then divide by whatever our new exponent would be, minus, as long as this has a power of 1, which it does, that's a natural log, and we don't have to worry about dividing by anything because that x has a coefficient of 1 also. This has a power of 1/3. As long as this has a power of 1 and a coefficient of 1, we don't have to worry about the inside and having to do u substitution or anything. We would just do x plus a 1 to the 4/3. We would divide by 4/3, and then we always want to do our plus c. So negative 1 over x minus the natural log x plus 4 in its absolute value, and then this would, that's a 4, yeah, 3/4, and then x plus 1 to the 4/3. All right, exponentials repeat themselves, so we would just say e to the 2x, and then we know we have to divide by 2. We're going to evaluate that from the natural log of 2 to the natural log of 4. I'm going to pull out that half, and then we're going to do e to the 2 ln of 4, and then minus your denominator, e to the 2 ln of 2. Some log properties here. The e and the natural log don't cancel just yet. We would have to take this 2 and then make that the power of 4. So we're done with that. So when we do that, now the e and natural log would cancel, but we're left with the 16. Similar in the second one, take this 2, make it the power of 2, so that it's no longer here, it's here. Now we can say our natural logs and exponential function cancel, and we're left with 2 squared, which is 4. All right, which will give us an 8. 13, if it's a definite integral, again, we've done this a little bit on and off in our reviews. Even in the current chapter we're having to do some antiderivatives. You get x squared over 2, natural log of x. Plug in the upper limit first. Simplify these, so these are 2 that we would want to know, although you'd have your calculator, I guess. Natural log of e is a 1, and then minus a 1/2. Distribute this to that, so we'd actually end up with a minus, but natural log of 1 is a 0. Combine those, you get e squared over 2 plus a 1/2. Okay, 14. I'd recommend rewriting this real quick when we have those negative powers and the fractional powers, and then do your power rule. It's easier. That way it's just too easy to mess up if we don't. So you add 1, divide by the new power. Same here, add 1 to that power, divide by the new power. And then don't forget your plus c, since it's now an indefinite integral again. So this one we would get 2 root x minus 3/4 x to the 4/3 plus your constant. 15, very much AP style of a question. So something that you would definitely want to make sure we're squared away on. When you're asked to evaluate a definite integral, or any integral really, where we know certain terms and we don't know other terms. So what I mean by that is we know what this is, it's a 4, but we're given a generic old f of x for that one. What that's typically testing you on is your understanding that we can split up integrals if we want to, if we need to. So in these, you probably want to. And that then means you're probably doing these 2 different ways. This way we can do it with, so this one here, I'm just going to do it with the way that we just did up at the top. Do your antiderivative from 1 to 3. Plug in your upper limit, we get 12, minus your lower limit, you get a 4. So we know that's going to evaluate to be an 8. Whereas over here, we don't know what our antiderivative of the function would be. But we do know that actual answer. If I integrate f of x from 1 to 3, then you're going to get a plus b. So this just right away is what we were given. We just write down an a plus b here, and then we find the sum of those 2. They're more creative than I am. A lot of times they get the same terms, or we're going to be able to add those together, but then that just is your answer. Really common. All right, these... The acceleration of a particle moving on a straight line is given by, it's our acceleration. I want you to find the position if we know an initial velocity and we know an initial point. We should understand position, velocity, acceleration. We're hanging out at the bottom right now. So if we did the acceleration as 2t plus an 8, the antiderivative of that would give us our velocity. So that would equal t squared plus at, and then your constant. We have to do the antiderivative, so now we're hanging out at our velocity, but we don't want to take our antiderivative yet until we know what that c is. So in order to figure out the c at this step, we would need a time, and we would need a velocity at that time, and that's what this is giving us. So this is telling us that our velocity is 6 at a time of 1. So 6 would equal 9 plus a c. So our c here is going to be, let me squeeze that in, as a -3. So then we can come up here. We can write our velocity equation in its entirety. T squared plus at minus a 3. Now that we know our velocity fully, we do our antiderivative of velocity to take us up to our position, which is the answer. So we do our antiderivative one more time. Call this what they want us to call it. So if you look at this, they want us to call it s. So we would say s of t is t cubed over 3. This would be 8t squared over 2, so 4t squared minus 3t, and then plus your constant. To figure this out, you now are going to use this information. We know at the time of 1, our position is 1. So let your position be a 1. Let all of our t's over here be a 1. What you should recognize here is the 4 minus 3 is a 1. It's going to cancel out that 1. So what our c ends up being is a -1/3. So our position function is t cubed over 3 plus 4t squared minus 3t, and then plus or minus, sorry. Your 1/3. And then that looks like a 7. It's not easy to write with this thing. I'll be happy when these days are over, and then now here this goes again. Here we are. It's a 1. All right, 17. We're going to have a whole packet on this differential equations soon enough, but this is where it popped up. So it says consider the differential equation given by, and then you're given this. Where x doesn't equal 0, says find the particular solution y equals f of x to this differential equation. So if you're given your derivative and you're told that the solution is y, or if the solution is your original function, then that means we need to do the antiderivative of that. So where this one's a little different than number 16, these are the ones where you have the same or different variables on the same side. And we need all of the y's on the left, all of the x's on the right. So it's when we said we first want to separate our variables. We do that, we would divide the y over. So what that leaves us with is dy over y minus a 1. And then that would equal x squared times dx. From there, we can now do our antiderivative. Once again, since our power is a 1 for this y and the coefficient is a 1, it's just a simple little natural log of y minus a 1. Definitely use your absolute values for this. It's all free response. If you don't have that, that's going to be a really bad point to lose. That would equal x cubed over 3, and then you're going to add your constant. You can go either way right now. I think most people find their c at this point. We can do that here. We know that if y is 3, actually let me do this over here. So now let your y be a 3. And when y is 3, we know our x is a 0. So the c for this problem is the natural log of 2. So now let's write what we had before. If we know this is our c, we would have had the natural log of y minus 1 equals x cubed over 3, and then instead of plus c, we now know that's a natural log of 2. Solve for y, so this is now going to be us using our exponential function. It will cancel this thing out, so we're going to get a y minus a 1. And then over here, this is our old algebra rule, where the reason we would be adding exponents is because we would have had two different e's being multiplied by themselves. So this now becomes a product between e to the x cubed over 3, e to the natural log of 2. So these would now cancel, and we're just multiplying by 2, and then we would still have an e to the x cubed over a 3. Solve this for y. All right, and then that's our guy. All right, 18, length of a curve. Here's another tricky way that they gave this. This actually was a similar way that I presented this to you on your test, making you do a problem like this, where it's a length of a curve, so we would have to know that formula from before. From 1 to 3 is given by that. And then I want you to find the equation of the curve. So we don't want a line tangent to the curve. We want to know the actual equation of this curve. And the curve passes through this point. So first and foremost, we've got to recognize the length of a curve is given by 1 plus your derivative squared. So if you were told that this here is in fact your derivative, then for us, from 1 to 3, we've got to think, what are we squaring to create this term right here? That hopefully is pretty easy to see. It's got to be the cosine of 2x. What that means is that's our derivative. So f prime is the cosine of twice x. So if that's our derivative, and we now want the actual equation of the curve, not the line tangent to the curve, keep that straight. Every year people come back telling me that they screwed up. They found the line tangent to the curve versus the equation of the curve. Here we want the equation. So that means we now want to do our antiderivative. That will give us the original equation. And then that would be sine of 2x. And then remember that we have to divide by that coefficient. So that's 2 plus your constant. The reason they gave you this point was not because you were writing a line tangent to the curve. You were given that point so that you could figure out what your c is over here. So let your y be the 3/2. I need to make this bigger so I can squeeze it in there. Oops. So let your y be the 3/2. And then when x or y is 3/2, our x was the pi over 4. So we'd get 3/2 is equal to what we're really looking for over here when we simplify this numerator. So let me tell you where I'm looking. So over here, what this really becomes is the sine of pi over 2. If we reduce the inside first, it's pi over 2. We then want the y coordinate at pi over 2, which is a 1. And then we would still have our 2 in our denominator. So the c, squeeze this thing in here, c is a 1. 3/2 minus 1/2 is 1. So the final answer then, we can now write this function. Let me just do it this way. We can come back up here. We can now, instead of this generic plus c, replace it with a 1. So this is our original function that would give us this length of a curve and also goes through this point. Okay, and last but not least, not quite last, almost last. Sorry to tease you. Tables. The last week when we review the types of questions that I think you would probably get, tables are definitely going to be one of them. I referenced that earlier with when we were doing trapezoid rule, Riemann sums, left endpoint, right endpoint, all that stuff. Really, really something that I, if I had to bet a little bit of money on, this would be kind of that other question, and then they just ask you a whole bunch of questions on it. Here again are a couple of them. This we've already done in the previous one. If I want you to approximate a derivative, so if you look up here, this is twice differentiable. The table above gives you values of f for selected points between 2 and 13. So here is f. You are asked to find the derivative of f. Well, you can't find the derivative of f, not the exact derivative, because we don't have the actual function. So we need an approximation method. So one of the things for sure, you're going to have to do is approximate your derivative. All the approximation of a derivative is your old slope. We just want it to be as accurate as possible. So the most accurate approximation for our derivative at 4, so if we come over here, here's where x equals 4 would have been. We want to use the points that are closest to that x value here. So that for us is x equals 3 and x equals 5. So we would want to do f of 5 minus f of 3 over 5 minus 3. And then f of 5 is a negative 2 minus f of 3, which is a 4. And then all divided by 2. So that we would say our estimate is a negative 3. So we can say f primed of 4 is approximately a negative 3. All right, and then b. This one you don't necessarily have to separate, but I just think as a general rule, when you are given something like this where one of them is written in literal terms, so by literal terms, I mean we don't know the function. It's just given it generically as an f, or g, h, or whatever. And then we know the other one, so like this we can actually do. I think as a general rule, what typically covers you pretty well is to just separate these and treat them as two separate problems. So that's what I'm going to recommend that we do here. So we're going to go from 2 to 13 and deal with 3 dx, and then we're going to subtract, go from 2 to 13 with the 5f primed of x. So with this one, we can do your antiderivative. This is also, I probably should have referenced that earlier. This is really just 3 times dx. The dx is the difference in your limits. So that would be 11. So this should give us a 33. If you don't remember that, just do your antiderivative like we've done now a bunch of times today. Do your antiderivative, plug in the upper limit, get 39, plug in your lower limit, you'll get a 6, but we get that 33 like we would if we just knew the little shortcut. Then whatever we get from the second one, we're just going to subtract from 33. So with this one now, understand where you're at. This is f prime. They're asking you to integrate f prime. So the way this is going to work, think about what would happen if we integrate f prime. The antiderivative of f prime would give us f of x, and then in this case we're going from 2 to 13. Well, that's what we're given in our table here, that these are functional values. So we can now, if we're dealing with f of x, use our table to get these values. So I'm going to have 5. I'm actually going to ignore that in this case. We'll pull it out. And then I would want f of 13 minus f of 2, whatever that difference gives us, we're going to multiply by 5. So f of 13, if you look at your table here, would have been 6. F of 2, looking at your table, would give us a 1. So we end up with 33 minus 25, so that our final answer would be 8. And then 20, last one, just to make sure we understand this idea again. we can split these up. I would again recommend doing that. This is the third time you've done this. I've had you do this twice. Once you had to reference a table. That's what we just did in number 19. The other time that I had you do it, I just gave you the values. And this one, now you're going to use your graph. So we're going to split it up. One of them you're going to have to use the graph for f shown to the right. The other one you're going to have to, we can do this normally. All right, we know the antiderivative of 4. If yours looks like mine, you're going to have to add these. So throw this in there. It should look something like this. Mine did not print out good, and that's what I saved for you. That graph should look like that. So we have the graph. This case, it doesn't do us any good to do the antiderivative of this, which you would have to do with like changing its case from A to D, because we have no way of getting capital F values. Like up here, we were able to go from F prime and write it as F because we were given F values in our table. This wouldn't do us any good if we did it for this problem. So we're not going to be able to do it for that. So let's get rid of this, maybe. We're just going to have to use our table. So if we look at our table, what this is asking you to do is to integrate this function, and I should label this as f. That's a key element to this problem. I want to integrate f. F, instead of a table of values like you had above, is now this graph. So when we do the integral of some function, that's the area, so that we have reviewed. We're looking for a value here. I would have to specifically spell out area. Even if I didn't put value there, it'd have to specifically spell out area. So what we would know is we have a positive 7 above, and then we would add the areas below. But the areas below we consider to have negative values. So the 7 plus the negative 5 that we have below tells us that this thing has a value of 2. And then we would add that to do our antiderivative of this from A to D. Upper limit plugged in minus your lower limit plugged in. Take this answer, take the answer from this. We add those together. Not much happens with this one. You just write it as the sum of those terms. All right. That is a wrap for this one. Again, thanks for bearing with me here. We have 3 more to go, 7, 8, and 9. And then number 9 is actually the chapter that we are currently on, the sequences in series. So really we just need to get through a couple more, and then you're through with me giving you all these reviews. So good luck with everything. If you have any questions, again, reach out.